Good afternoon, everybody. Welcome to this seminar that we're hearing, which has been given by Professor G.P. Das from the Indian Association for the Cultivation of Science in Kolkata. So it's a great pleasure to introduce GP. We're going to have a very interesting presentation on epitaxial heterostructures and quantum structures, expectations and challenges, which I guess is what it says up there, yes. So GP has a wide range of experience over many years on nanostructures and quantum structures, and he's spent several years at the Max Planck Institute in Stuttgart, where he was studying nanostructures and DFT. He's led a large number of international associations in a number of areas. Just trying to see a couple of examples here. Oh, I'm looking at the wrong one. That's why I can't see it. The Materials Research Institute in Sendai, Virginia Commonwealth University in Richmond, and also, as I said, the Max Planck Institute in Stuttgart. And he's led several associations in computer material science, Asian Hydrogen Storage Initiative, and the Coordinated Research Program on Spintronic Materials. So I think we're going to have a very interesting talk from GP. We're going to hear a wide range of information about DFT applications to nanostructures and spintronics and hydrogen storage. And so with that, I'm really looking forward to this talk, GP. Thank you very much.
Thank you, Gavin, for this generous introduction, I'll say. So the talk that I am going to present is Epitaxial Heterojunctions and Quantum Structures, Expectations and Challenges. Well, before I start the talk, let me tell you this particular volume, Physics in the New Era, states that there are 4 areas or broad categories that are coming up as the most important directions in science, in physics in particular, namely quantum manipulation of new materials, complex systems, structure and evolution of the universe, and fundamental laws and symmetries. Today, we are going to concentrate on the first one, namely the quantum manipulation and new materials. The emphasis on the unity of the field and the strong commonality that links the different areas will be highlighted. And there are a lot of new and emerging areas which are coming up. Well, the role of quantum mechanics, right from the aerospace applications to quantum computers, are coming up today, which falls under the broad category of quantum manipulation of new materials. Those of you who are interested, you can have a PDF version of this particular volume from the National Academy Press. Now, why I mentioned about it is the following. We are talking about playing with materials that are given in the nature. Question is interface between two materials different from the materials as such? What are the novel interface-induced phenomena that are appearing? And last but not the least, how do quantum effects play a role? I have given here 2 very well-known examples, namely gallium arsenide, aluminium arsenide quantum well, which most of you are aware of. This is what was the starting point for the quantum Hall effect. And there is also the 2D electron gas, which is developed at the juncture between the 2 semiconductors. So by controlling symmetries and atomic arrangements at interfaces of complex materials, we will have a tremendous opportunity for searching for novel phenomena which do not exist in natural compounds. Starting from something which is there in the textbook, quantum confinement is well known. It gives rise to discrete states, and the energy levels for a particle in a box can be obtained by simply solving the Schrödinger equation. And sorry, and in one dimension, if you solve it, you can easily get the energy spectrum. In fact, you can get the density of states in 3D, 2D, 1D, and 0D, and it is well known how the behavior of the density of state changes from 3D to 0D, and that is given here in this table. At IACS, the institute I come from, we have a Center for Quantum Structures, which is a focused experimental computational research initiative on charge and spin transport in physically assembled quantum structures and devices. And we have the facilities such as molecular beam epitaxy, photoemission electron microscope, VT-STM scanning tunneling microscope, SQUID VSM, micro Raman, ultra high vacuum sputtering, MOOC, and so on and so forth. The plan of my talk today is as follows. I start by giving you an introduction to modeling and simulation using DFT. And then I will specifically come to the modeling of A-B epitaxial interfaces. You have got two solids, A and B. When you form an epitaxial interface or a heterojunction between A and B, what are the ways in which we can handle, and how DFT can be, for example, used to estimate quantities. One of the examples which I will give you is a Schottky barrier height in metal semiconductor interface. Then I'll come to manifestation of some novel properties in 2D. The case studies that I would like to cover are mentioned there, silver on silicon 111. Then I'll come to some quasi two-dimensional material, silicene on 3,5 and 2,6 semiconducting substrates. Hexagonal boron nitride sheet on nickel 111 is an example for oxidative catalysis. And finally, I will mention about molybdenum disolenoid, a layered transition metal dichalcogenide on a metal substrate, and we have taken nickel 111 and copper 111 for reasons which will be clear as I go on. Let me start with an introduction to the modeling and simulation. Now, materials are complex many-body systems, and equations that describe the physical and chemical behavior of real systems are often too complicated to be solved analytically or even numerically. And the key assumptions about reality can be made often ignoring the complexity. So what is modeling? That establishes a relation between physical or chemical quantity, and simulation gives the numerical solution to the model applied to a specific situation. This one, which I have taken of course from the Google, the real system can be treated via experiment, obviously, which most of us are doing, and it can be parallelly modeled for simulation. In particular, for AB epitaxial heterojunctions and superlattices, we do synthesis via molecular beam epitaxy or MOCVD or laser ablation, which is also sometimes called laser MBE, and many other advanced techniques. Parallelly, the modeling and simulation of those interfaces are done using first principles DFT, which is the subject matter of my talk today. Let's look at the types of interfaces, the broad categorization, and what are the physical quantities that can be expected from these interfaces. Metal semiconductor interface is something which is essential for understanding Schottky barrier. Semiconductor heterojunctions or semiconductor-semiconductor interface, the physical quantity is band offset. Again, something which is very important in device. Insulator semiconductor interface, for example, in MOSFET devices, as you all know, or in MESFET devices, interface state plays a crucial role. In metal ceramic interface, chemical bonding between two completely dissimilar, electronically dissimilar materials, namely metal and ceramic, how do they get bonded? GMR is something which is extremely important phenomena, which, as you all know, appears in metallic multilayers. For example, ferromagnet, non-magnet, ferromagnet, metallic multilayers give rise to the GMR effect, which is well documented in the literature. And finally, I have written spintronics, that is spin electronics, which is coming in a ferromagnet semiconductor interface. So this vast diaspora of epitaxial interfaces are giving rise to different physical quantities. Interesting thing is that the DFT based computational approach can be very successfully used to handle these wide ranging variety of interfaces. And usually these calculations are supercell geometry with the necessary boundary conditions along the z direction that is perpendicular to the interface. We usually do local density approximations, or LDA, or local spin density approximation, and its improved ramifications such as generalized gradient approximations, hybrid functionals, and many of the exchange correlation functionals that are used in the literature. One can use plane wave based methods or localized basis set methods. I will not go into the details, but VASP, that is VASP, Vienna ab initio simulation package, with projector augmented OA potentials are routinely used for many of the applications, some of which are going to be discussed in my talk. The rest of the things, whatever I have written, are some of the technical details which we can skip. This is something which I have shown as a benchmark. As you all know that in nanoscience, one of the most important discoveries is scanning tunneling microscope. It took about 2.5 decades to understand the reconstruction of a pure silicon 111 surface, the 7x7 reconstruction it is called. And this is a ball and stick model of a 7x7 reconstruction of silicon 111 surface, which Binnig and Rohrer way back in 1983 solved using the scanning tunneling microscope. What is interesting is that when we do a DFT calculation, it exactly reproduces the 7x7 reconstruction. What you are seeing here is the charge density contour of the 7x7 silicon 111, pure silicon 111 surface under ultra high vacuum. So that essentially proves the success of DFT in probing surfaces, interfaces, and superlattices. Something which one has to keep in mind is that when we have an interface, there is a perturbation caused by the very presence of the interface, because you have got two different materials A and B, and you have got a junction where there is a discontinuity. The perturbation obviously dies down asymptotically into the individual solids a few layers away from the interface. And most of the interface induced physical properties are dictated crucially by the exact geometry and the electronic structure of the interface. And there is a self-consistent intertwining between the geometry and the electronic structure. The model calculations that rely only on the electronic structures of the two bulk constituents obviously fail to explain and reproduce the experimental results on these heterojunctions. Now this is a very important point because a crucial role is played by what is known as the interface-induced dipole. The interface-induced dipole at the junction or at the heterojunction can be calculated. Whatever you are seeing here, this delta rho is when you subtract the rho of the metal semiconductor junction and the two individual rho means the charge density, the electron density for the metal and the semiconductor. So when you subtract the charge density of the metal and the charge density of the semiconductor from that of the metal semiconductor interface, you get the delta rho, which is responsible for calculating the interface induced dipole, and this is very, very important. Now coming to this example of metal semiconductor epitaxial junction, which is nothing but a 2D quantum structure, and it is a fundamental constituent of electronic devices, there are several very interesting things which are discussed in the literature. For example, what are the localized surface and interface states? The metal induced gap states, I'll give you some example, it is called MIGS. Work function of the metal overlayer, which obviously is a surface property and can be exactly determined experimentally and also can be calculated using DFT. Schottky barrier height, which I will come into some more details soon, and the role of Fermi level pinning. Let's look at this cross-sectional TEM picture of epitaxial interface between nickel disilicide and silicon. See, this is silicon 111 and this is nickel disilicide and this is the interface, and it is interesting that silicon and nickel disilicide have almost the same lattice constant. One is a metal and the other is a semiconductor. So this particular interface is responsible for the Schottky barrier height. And here this band diagram shows you there is a Fermi level on the metallic side and there is a conduction band and valence band. So you can find out the work function at the interface from this formula W equal to E vac minus EF, and the p-type Schottky barrier height can be obtained by subtracting the EF from EV. So the EF is the Fermi level and the EV is the valence band top. So if you subtract EF and EV, you get what is called the p-type Schottky barrier height. The experimentalists usually quote the n-type Schottky barrier height, which is nothing but EC minus EF, but the two Schottky barrier heights together, the n-type and p-type, is nothing but the gap of the semiconductor. Now why am I discussing this? I am discussing this because of a very intriguing observation in Bell Labs way back in the late 80s, that in this particular interface, epitaxial interface of nickel disilicide on silicon, depending on what is the orientation at the interface, it's called A type and B type, the Schottky barrier height changes enormously. The p-type Schottky barrier height for A-type NiSi to Si silicon interface 111 is 0.52, whereas for the B-type it is 0.38. Imagine that I am not changing the semiconductor, I am not changing the metal. So there is no question of my changing the work function, but still the Schottky barrier changes by as much as 0.14 electron volt, which is something which could not be explained at that time. But that experiment in Bell Labs was one of the most important landmarks in device physics. Just to explain to you what is A type and B type, I have given you this ball and stick model. You can see that here in an A type interface you have got the silicon 111 and this is NiSi2, whereas here the NiSi2 is 180 degree rotated with respect to the silicon. So these are called A-type and B-type geometry. And we have done a DFT calculation for both these interfaces to calculate the Schottky barrier height. Before I tell you the result, something is very important, namely, what is the interface structure? At the interface, it is possible that the metal atom, what is the metal atom here? It is nickel. The metal atom, which is in this particular case the blue one, is bonded to the silicon. Here, the silicon of NiSi2 is bonded to silicon of silicon 111. So there is a difference between this and this. It is called 5-fold coordinated surface, 7-fold coordinated surface, and 8-fold coordinated surface, which essentially means how many nearest neighbor atoms are there for the metal. That makes a difference in the Schottky barrier height. See, this is very important and very interesting. How crucial is an electronic quantity like Schottky barrier height on the geometry of the interface, which is epitaxially grown, let's say, using MBE. Now, there have been very accurate X-ray standing wave experiment in Hamburg. These X-ray standing wave experiments have shown whether in case of nickel disilicide silicon, it is 5-fold or 7-fold or 8-fold. And I will tell you the result. In case of nickel disilicide, it has been established that it is a 7-fold coordinated structure using X-ray standing wave. Whereas in case of cobalt, it's a 8-fold structure which has been established. Let us now look at the binding energies of the 5-fold, 7-fold, and 8-fold coordinated interfaces of the NiSi to Si. Look at the numbers. And it is possible for you to see which one is the most stable. For NiSi2, the most stable is the 7-fold coordinated. You can see that. This is the one. Whereas for cobalt disilicide, it is the 8-fold coordinated, which is the most stable. And these results are consistent with the literature. This is the last slide where I will show you how we estimate using DFT the Schottky barrier height in A and B type NiSi to Si epitaxial interfaces. This work was done way back, but this is one of the first work which was done on epitaxial NiSi to Si interface, and you can see that this is the interface here, and this is the silicon 111, and this is the NiSi2, and this is the self-consistent charge density contours, and here is the interface. This is the A-type interface, this is the B-type interface. And if you compare the value of the Schottky barrier height for the A-type and the B-type interfaces, you can see that the difference between the A-type and the B-type interface, our calculation shows 0.12 electron volt, which is very close to what the Bell Labs experiment showed, which is 0.14 electron volt. I will not go into further details as to how actually we calculated this delta Q, which is nothing but which is obtained from the interface induced dipole. But the results show the triumph of the density functional theory in establishing the orientation dependence of Schottky barrier height. Now I'll come to another example, which is not lattice matched like NiSi to Si, but it is lattice mismatched. For example, silver on silicon 111. If you look at the lattice parameter of silver, it is 4.09 angstrom. That of silicon is 5.43 angstrom. This is a huge lattice mismatch, nearly 25%. Now, it is possible to do a kind of an epitaxy where there are 3 by 3 unit cell of silicon is placed on a 4 by 4 unit cell, surface unit cell of silver. And that is exactly what is shown here. You can see that here there are 1, 2, 3, 4 by 4 surface unit cell of silver, and whatever you are seeing in the golden color are, you can see 1, 2, 3 by 3 in the substrate, which is silicon. So this kind of an epitaxy results in reducing the mismatch to almost 0.3% lattice mismatch, and this is what is called coincidence site epitaxy. You can see that coincidence site epitaxy of silver silicon. We have done a full-fledged DFT calculation on this kind of a interface, and you can see interesting manifestation of metal induced gap states. See, whatever I am showing here are the layer projected density of states. You can see that the one which is here is at the interface. So this is the silicon at the interface, and as you go away, this is the silicon which is farthest from the interface, and you can easily see that the one which is farthest from interface has got the traditional 3-humped structure of silicon with a gap. However, when you come closer and closer and closer and closer to the interface, you can see that there are states, localized surface states or interface states which are developed, and it is those interface states which are responsible for the pinning mechanism. And we have done the detailed study of this kind of a silver silicon interface. I am only going to show you the results, namely look at the work function for, here are the work function values for silver 100, silver 110 and silver 111 using LDA and GGA, and they match reasonably well with the last column is experiment. This is the LDA value, this is the GGA value. Okay? And here are the values for the Schottky barrier height, which is 0.54 p-type Schottky barrier height, which is 0.54 electron volt for the silver silicon 111. And obviously, if you subtract from the silicon band gap 1.1, you get 0.56 electron volt, which is the n-type. So you can see the p-type and the n-type Schottky barrier height, and this matches very nicely with experiment. Here are the charge density contours, which is very interesting because you can do it only by doing a DFT calculation, and it is clear that, look at this, 5 surface atoms of silver on 4 surface atoms of silicon, 1, 2, 3, 4. So the nature of bonding between silver and silicon is something which is shown very clearly by this self-consistent charge density contour. Whereas when you go further down, that is in the silicon side of the interface, you can clearly see the covalent bonding in the silicon 111. So the charge density contour clearly establishes the kind of an asymmetry in the surface charge densities, and you can see the right half of the charge density and the left half, they have got an asymmetry. So to summarize this particular part of my talk, I started with a benchmark for silicon 7x7 reconstruction, and then I told you about the interface relaxation and how the metal induced gap states appear in the layer projected density of states, and we have also estimated the p-type Schottky barrier height in the metal semiconductor junction. Okay. Now I will shift gear and I will tell you something about spin-based electronics. Time will not permit me to go into any details of this on which there is a huge amount of work which is already there in the literature, but I will just touch upon something which we are trying to do without going into any details. So spin-based electronics is nothing but a controlled transfer or injection of spin polarized current from a ferromagnet into a normal metal or a semiconductor. Okay. Now, as we all know that in case of metallic multilayers, there is manifestation of GMR and TMR, and on GMR there was Nobel Prize in '88 to Peter Grünberg and Albert Fatt. There are all semiconductor structures which leads to diluted magnetic semiconductor. Here it is DMS, the diluted magnetic semiconductor, and Hideo Ono's group in Sendai has done pioneering work on the DMS. And there are hybrid structures combining metallic ferromagnets and semiconductors such as iron magnesium oxide iron, where the TMR ratio goes very, very high, up to 500% or even more. And each of these systems which are used for spin-based electronics have their merits as well as limitations, and these are vigorously being pursued by experimentalists as well as theorists all over the world. This is a textbook example today by Supriya Datta in Purdue, who came up with this idea of what is known as the spin field effect transistor, the spin FET. So according to the principle of this Datta Das, this is in APL 1990, spin FET, electrons would be injected from the source which would align the spins so that their axes were oriented in the same way as those in the source and the drain. So you are actually injecting spin polarized current from the source to the drain via the gate. And the details, those of you who are interested, you can have a look at this beautiful paper. It's a short paper by Supriya Datta and his colleagues on spin FET. Again, this is a glaring example where how the interface induced effects play a role. In order to exemplify this, I'll give you a Mickey Mouse picture of iron gallium arsenide 001 interface, and what we have done is a kind of a delta doping. Experimentalists, they know what is delta doping. Delta doping means what we do is that at the interface between the metal and the semiconductor, in this case the semiconductor is 3,5, we dope one layer of some other material, some other metal such as manganese. So you see here manganese is doped close to the interface. This is called a delta doping. Okay, and because of this delta doping, we have established a spin current and also the development of magnetic moment in iron manganese gallium arsenide interface. This work is something which is going on, so I do not want to go into further details, excepting to tell you that the magnetic moment shows an enormous kind of an increase because of the delta doping. Now I come to the last part of my talk, where I'll mention about the 2D materials which span a whole range of electronic behavior. We all know in the post-graphene era, the 2D materials are becoming so important, both from the fundamental as well as from application point of view. And many of the materials whose corresponding 3D counterparts were known for ages. People know graphite, silicon, germanium, phosphorus for ages. But it is only in the last 10 years or even less that we come across graphene, silicene, germanium, phosphorine. Then there are 3,5 semiconductor sheets like hexagonal boron nitrides, or 3, 4, 5 sheets, or layered transition metal dichalcogenides. And the interesting thing is that all these 2D materials, they span a whole range of behavior, starting from a conductor to an insulator to a semiconductor. Well, that is not the end of the story. People have tried to put two or more such 2D materials one above the other like a sandwich structure, and that gives rise to what is known as the van der Waals heterostructure. I would like to say a few things here. See, those people who are doing, for example, MBE, now there it is mandatory that at the interface the strength of the bonding between the overlayer and the substrate is above a certain value. In these cases, in the van der Waals heterostructures, the bond between two layers is relatively much weaker, and that is why this class of materials are termed as a van der Waals heterostructure. So these are very weak bonding, and that is why it is possible for you to either exfoliate or put one on the top of the other with a lot of freedom. And all this entire field is an emerging paradigm in material science and device physics. I will touch upon just one or two examples. The first example which I am going to take is a work which we have done relatively recently, namely silicene, epitaxially grown on 3,5 and 2,6 semiconducting surfaces. Let me dwell upon this silicene for a few minutes. Silicene looks like graphene, but not exactly. It is also this kind of a honeycomb structure. However, there is a buckled geometry, as you can see here. There is a buckling. There is a buckled geometry. Unlike in case of graphene, which is completely 2D, the infinite sheet. However, in case of silicene, there is a low buckling geometry, and this value of the delta is approximately half an angstrom. So there is a partial sp2 hybridization, unlike graphene where it is complete sp2 hybridization. And well, I mean, people have done its band structure for the freestanding as well as for silicene on different kinds of substrates. Now, my intention in this lecture is to tell you about what happens when you put silicene on a substrate, and what is the substrate induced phenomena that takes place. Well, these are all things which are from the literature. These are not my work. So you can see that silicene freestanding as well as supported, how the linear band dispersion and the Dirac cone, and this is the ARPES measurement which shows the apex of this cone, which is lying about 0.7 electron volt below the Fermi level. And these are the band structure and the density of states which are very well known for silicene today. Silicene has been successfully synthesized on different kinds of metallic and insulating substrates. Metallic substrates which have been tried upon are silver 111, maximum work has been done on this, also on iridium 111. And insulating substrates that have been tried are hexagonal boron nitride, silicon carbide, zirconium diboride, and so on and so forth. Graphene substrate has also been tried upon, but I am going to tell you about the last one, namely the semiconducting substrates, which is either 3,5 or 2,6 semiconductor. Now the criterion is that there should be limited intermixing between the silicon and the substrate. What I mean is the following: if there is a very strong bond above a certain value, then the linear band dispersion characteristic will be completely lost. So what is needed is to have a nominal bonding between the silicene and the substrate on which you are depositing the silicene. Let's take the example of silicene on silver 111 substrate. This work has been done by the group of Gilles in France, and look at the value of the binding energy. The binding energy is about half an electron volt, and the DFT calculation yields a Dirac cone which is about 0.3 to 0.5 electron volt below the Fermi level. And it also results in a root 3 superstructure which is absent in either graphene or hexagonal boron nitride. Now, as I told you that we tried semiconducting substrates to grow silicene. So when you try to grow silicene on either 2,6 or 3,5 substrates, then you have to remember one thing. Is the silicon of the silicene getting bonded to the metal or to the non-metal? So it can get bonded to zinc or it can get bonded to sulfur. Depending on whether it is metal terminated surface, like here for example, you can see that this is a metal, zinc. This is a silicene, this is a metal. So the other side is a non-metal. Whereas if this is a non-metal terminated surface, then the other side is a metal. That makes a difference, because what happens is that if it is a metal terminated, then the other side is a non-metal, and obviously then you have to passivate it with hydrogen in order to ensure that the dangling bonds are passivated. However, if it is a non-metal terminated, then the other side is a metal, and then you don't have to bother about the passivation. So we have done the calculation for both metal terminated as well as the non-metal terminated silicene. Here is the silicene. This is the interface. So this is the silicene on metal terminated, and this is the silicene on non-metal terminated. And here is the ball and stick model for that. Okay. Now, thankfully, the lattice parameters of silicene with most of these 3,5 and 2,6 semiconductors are reasonably good, not exact, but reasonably good. So here is how the binding energy of the silicene layer epitaxially grown on the 3,5 and 2,6 semiconductors behave. These are the numbers you can see here, and this line is the binding energy for silicon on silver 111, which Gilles' group have got. So 0.52. Whereas our results, the binding energy varies from 0.44 to 0.68 electron volt. Okay, so this is the these are the range of values for the metal terminated surface. For non-metal terminated surface, the range is somewhat higher for the binding energy, but nevertheless these are around the half an electron volt line for the metals. Another interesting thing is that there is some magnetic moment which either gets enhanced or quenched depending on what is the substrate. As you can see that for aluminum arsenide, aluminum phosphide, gallium arsenide, etc., when you put these silicene on the 3,5 and 2,6 semiconductors, the magnetism gets quenched for aluminum arsenide, aluminum phosphide and gallium arsenide. Whereas for gallium phosphide and zinc selenoid, interestingly you can see that the magnetism gets enhanced. Whereas for zinc sulfide, this is neither enhanced nor quenched, it is 0. Work function is something which is very important from the point of view of doping. So we did the calculation of the work function for the p-type, for the metal terminated as well as the non-metal terminated systems, and the one which is the red circle, these are the non-metal terminated systems, and you can see that the value of the work function is more than that of the freestanding. So it is a p-type doping. Whereas in case of a metal terminated, the black square ones, the value of the work function is lower than that of the freestanding, and so it is the n-type doping. So you can ensure either p-type or a n-type doping depending on whether it is a metal terminated or a non-metal terminated interface. So again you can see that the interface induced manifestation of the doping is something which is coming here. So what is the take home message for this? The take home message is the following. The binding energy of silicene on metal terminated surface is coming out to be approximately 0.56 plus minus some error bar. Okay, and the corresponding value for silicene on silver 111 was 0.52. So it is close. Silicene on non-metal terminated surface are all semiconducting substrates, leads to enhancement of magnetic moment, which I showed you. In case of metal terminated surface, it can behave either metallic or semi-metallic or even magnetic, depending on what is the choice of the substrate. And finally, I told you that it undergoes substrate induced p-type doping on non-metal terminated substrate, while it can be p or n-type doping on metal terminated substrates. It depends on the direction of the charge transfer. Okay. How much time do I have? Another 5 minutes?
We're 7 minutes to the moment. So
Okay. Okay. So I would like to take this example of oxidative catalysis. This is something which is again a very interesting manifestation of interface induced phenomena. Hexagonal boron nitride is an inert material in the sense that if you try to bring oxygen onto a hexagonal boron nitride surface, it will not like to get adhered. However, something very interesting takes place when the same hexagonal boron nitride you put on a nickel 111 substrate. Let me show you pictorially without going into any detailed numbers. See, a freestanding hexagonal boron nitride sheet is this one. When you are trying to bring an oxygen molecule O2 to that and do a full-fledged ab initio molecular dynamics, we find that, unfortunately I do not have the video, otherwise I could have shown you that what happens is that the oxygen does not like to stay, it goes away from the surface. This is for a freestanding hexagonal boron nitride sheet, so it is inert. However, when you put that hexagonal boron nitride on nickel 111, and fortunately there is a very good lattice matching between nickel 111 and hexagonal boron nitride. So we carried out the simulation of hexagonal boron nitride on nickel 111, and here you can see the nickel 111 substrate. This is the nickel 111. Here is the hexagonal boron nitride, and then we brought the oxygen molecule on this. We found that it is not only getting adhered to the surface, but also the oxygen bond distance increases from 1.32 to about 1.51 angstrom. You can see that there is an elongation of the bond of the oxygen bond. It was 1.32 here, and now when you put it onto the HBN deposited epitaxially on nickel 111, then not only that it gets adhered, but also the OO distance elongates to 1.5 angstrom, and it has a tendency to get bonded to the boron and not the nitrogen. This can be easily explained from the electronegativity argument. So this is an example of a substrate induced activation or modulation of electronic structure. We have done the details of the spin density plots and all these things, but I will skip those things for lack of time, and I will only show you the final result, namely when we have a CO molecule coming to the surface, what happens? Let us see. So now I bring a CO molecule to the surface, and it is interesting that the CO molecule takes away one of the oxygen atoms from the activated OO bond and goes away as CO2. You can see that. When the next CO comes, so here CO2, so CO comes, takes away an oxygen and becomes CO2, leaving behind one oxygen. When the next CO comes, it takes away that oxygen and again goes away. So finally, both the CO2 goes away, leaving behind the pristine HBN sheet deposited on nickel 111. So this is an example of an oxidative catalysis of a system which is costing almost nothing. You don't need any platinum or anything like that. This is almost free of cost. You are getting a surface which is behaving like a oxidative catalysis for CO oxidation. Okay. Now this part I will skip because these are some of the latest results which are still not published but about to be published. Well, I will say that it is in the process of getting published. So we have done very recently something on electron doped C2N monolayer as an efficient noble metal free catalyst for CO oxidation. Similar argument like HBN, but I think I will skip that, excepting to tell you this is a very interesting system. Like porphyrin, it is this C2N structure is a stable structure with it is like a holy graphene, you can see, and it is possible for us to dope it with oxygen, and when you dope it with oxygen it becomes it behaves like a catalyst, and we are just working on this. I will skip this part. Yeah. So the last 1 or 2 minutes, I will give you an example of how in a transition metal, layered transition metal dichalcogenide like MOS2, AC2, molybdenum diselenoid, MOAC2, how the electronic, magnetic as well as the chemical properties of the MOAC2 monolayer gets modulated because of the existence of a substrate. So it is a substrate induced modulation of electronic, magnetic and magnetic property. Now MOAC2 monolayer is a direct gap semiconductor with a band gap of about 1.5 electron volt, and it is important for optoelectronic and solar applications. Okay. Now when you make a heterojunction of MOAC2 on nickel 111, then what happens that because of the lattice mismatch, about 35% lattice mismatch, again what we did is this coincidence site epitaxy, which I already told you earlier for the case of silver on silicon. So here the 3x3 surface unit cell of MOAC2 is put on a 4x4 surface unit cell of nickel 111, and the resulting mismatch becomes almost negligibly small. The binding energy is about 0.3 electron volt per MOAC2 formula unit, and this is how the on top view shows. You can see 1, 2, 3, 3x3, and here it is 1, 2, 3, 4, 4x4. So this is the side view of the interface of the MOAC2 quasi 2D monolayer and quasi 2D layer, you can call it, on the nickel 111. And the electronic structure shows very interesting thing. When you do it on a monolayer MOAC2, this is how the density of state looks like. And you can see the red one is the partial density of state of selenium, and the blue one is the partial density of state of molybdenum, and you can see a LDA gap which is obvious. Okay, MOAC2. Now what I do is that I put a nickel 111 substrate, okay, and this is the interface between MOAC2 and nickel 111. Now lo and behold, what happens to the density of state? You can see that there are states which are developed in the gap. You can see that clearly. There is no gap anymore. Earlier there was a pure the gap, the LDA gap, whereas now as soon as you put nickel 111, there are states, and these states are metal induced states obviously, but more important is that these are not localized state, these are delocalized state. As you can see that these are delocalized all throughout. If it is a localized state, which I told you at the time of Schottky barrier height, it leads to pinning mechanism. However, here it's a completely different physics. Here it's a delocalized state, and this delocalized density of states is a signature of a good electron mobility across the semiconductor metal heterojunction. And there is also a substrate induced spin splitting in the overlayer density of state which we have found. So obviously there is a charge transfer, and in this case the charge transfer is from the metal to the TMDC, the transition metal dichalcogenide, and there is a decrease in the work function as soon as you are putting the substrate. From 5.45 eV it goes to 4.9 eV, okay, and this is also characterized by the N-type doping and is a signature of chemical modulation. So how is the chemical modulation taking place? I am telling you. See, I put a hydrogen on the top of the MoAC2, and this is how the charge density contour plot looks like. So when you are putting a hydrogen, you can see the hydrogen is getting bonded to selenium, and these are the contours, the charge density contour, self-consistent. Now what I do is that I put the nickel substrate and the interface, and again redo the calculation with, now there are the charge density of the substrate also appearing here, and the interesting part is that there is a resulting change in the strength of the bonding between selenium and hydrogen. And how much it is? It is pretty huge. The binding energy of the hydrogen with the surface increases from 0.3 to about 0.8 electron volt. And there is an accumulation of more charge along the selenium hydrogen bond in case of the supported MoAC2. And the chemical reactivity of MoAC2 monolayer gets significantly enhanced due to the presence of the nickel substrate. Well, I think I have come to the end of my lecture almost. I would like to summarize what I have tried to say in course of this lecture. I started with the DFT based first principles approach, which is ideal for investigating various atomically abrupt epitaxial heterojunctions, and thanks to the advanced techniques, experimental techniques which are available today, it is possible to realize these epitaxial interfaces under ultra high vacuum condition. So DFT can serve as an ideal complementary tool to establish the how accurately it is possible for us to reproduce these the experimental quantities which I already told you. It is not only reproducing the experimental quantity, but also to predict the values of the corresponding physical quantities via the DFT calculation. So we started with the Schottky barrier height example, and the role of the interface induced dipole, which is crucial for estimating the Schottky barrier height. In fact, I did not discuss that, but in the band offsets in semiconductor, not only the Schottky barrier height, but also the band offset in semiconductor heterojunctions crucially dictated by the interface. Then I came to another example, namely silver overlayer on silicon 111, where the metal induced gap states, the work function, etc. Are found to be very nice agreement with the experimental results. The epitaxial silicene monolayer on the 3,5 and 2,6 semiconductors can behave metallic or semi-metallic or even magnetic depending on the choice of the substrate. And towards the end, I told you about the hexagonal boron nitride on nickel 111, which serves as an oxidative catalysis. And finally, the molybdenum diselenoid on nickel 111 and copper 111 is an example where the delocalized interface states leads to increased mobility and also chemical functionalization of the surface. So that is where I end my lecture today. But it is interesting really that we can today grow almost any kind of 2D materials whose corresponding 3D counterparts were known way back. For example, molybdenum disulfide, molybdenum diselenoid, etc. These are transition metal dichalcogenides which were known several decades ago, and we are now almost rediscovering the corresponding 2D counterparts. So a stage is coming soon when you order a 2D material with a desired set of properties and you get it synthesized. So the most exciting material in the 2D diaspora may yet to appear in the horizon. So with that, I would like to thank you for your patience, and I shall be glad to answer any questions if you have. Thank you very much.
Well, thank you very much, GP, for that very interesting exploration of 2D materials, their interfaces, and the ways they can be manipulated and modeled with DFT. So we have time for some questions. Yes.
Thank you, Professor. May I ask, have you ever applied synthesis of nickel-111 in experimental synthesized situation? Or is it all theoretical by the DFT?
Oh, there are attempts to grow many of the materials, graphene, hexagonal boron nitride. They have actually been grown already on nickel-111, and particularly nickel-111 and copper-111 are maximum used because of the fact that there is a very good lattice matching between the nickel-111 and the graphene and hexagonal boron nitride, and that is why these are the most popular substrates. So these have been already done. Yes.
May I ask, what's the procedure for synthesizing this monolayer?
Okay, now there are many ways in which it can be done. To the best of my knowledge, as of today, probably the CVD method is by far the best method, even though I know that there are other techniques which people are trying to use. But for this particular class or family of materials, I think CVD is probably the most versatile technique for growing these materials. Yes. Yeah.
Okay, this is not a question, just I would like to know from you. Most of the silicon device, people start making on the silicon 100 surface. But you study silver or other layers of silicon 111 surface. What is the reason behind that?
Actually,
why you are away from the device real?
Okay, now you see, the point is that for many of these semiconducting devices, whether you take the 100 or the 110, let's take for example gallium arsenide, people have taken 100 and 110 both, because it depends on whether you want a polar surface or a non-polar surface. In case of a silicon 111, there is, historically speaking, most of the experiments which I pointed out have been done on silicon 111, and the reason is simply the following, that in case of nickel disilicide example which I gave you, the lattice matching is exact, almost 0%, almost 0.5%, almost 0, between NiSi2, which is a calcium difluoride structure, CaF2 structure, with silicon 111. And to the best of my knowledge, the X-ray standing wave experiments that were done in Hamburg, DESI, in Deutsche Elektron- und Synchrotron, were done on silicon 111, not 100. Okay? Because the density of the the surface atoms is different for 111 and 100. You are right that there are many devices which are done on 100. You are right.
Most of the silicon device 100.
100.
Yes. Give the less interface defect, you make the MOS transistor or any other device.
Maybe
compared to the 111.
Is that DFT a general method to calculate the two-dimensional materials, or you need some special techniques to consider the van der Waals force?
To consider what?
The van der Waals force.
Van der Waals forces.
Oh, yeah. Okay, good question. It's a very good question. It's a very relevant question. Yeah. So we use DFT as quote unquote the general tool, but you are right. For many of these materials that I mentioned, you do need to incorporate the what is known as the dispersion correction or van der Waals correction, okay, because they are weakly bonded. So just by doing a DFT calculation with the exchange correlation functionals, whether it is LDA or GGA, is not sufficient. We have to incorporate the in many cases, not in all, in many cases we have to incorporate the effect of the dispersion correction, and we have done that in this. So the methodology that we used are all DFT methodology using the appropriate exchange correlation functional plus the dispersion correction due to the weak bonding. If you do not take into account the dispersion correction, you may not be getting a very realistic estimate of the binding. So you are right, you have to incorporate the, but the broad framework is still within DFT.
I had a question on the silicene silver interface compared to the silicon silver interface. They're different interfaces, of course, but there's an interesting comparison between them, I think. With the silicene, the bonding is much weaker because it's mainly to sp2 hybridized.
Yes.
But the remaining bonds that are sticking down, they're slightly high bonds, I guess, which are orienting with the silver cell.
Yes, yes. So the on the substrate side, see the two examples that I gave you. One was silver deposited on silicon 111, and the other example which I gave you is silicene on, let's say, nickel or some other substrate. Okay, so the dangling bonds at the surface, yeah, that is there, but the one which is towards the substrate, that has already been saturated by the atoms which are there below the surface.
Yes.
They are saturated. Okay, and as far as our calculation is concerned, we have kept a huge vacuum on the top. The side which is, say, what you are calling an ultra high vacuum, in the terminology of a simulation person, what we do is that we create a vacuum, and we have well defined way to create a vacuum in such a way that there is no way that the surface atom has got any other foreign atom with which it can, so it's completely a pure surface, yeah, that we can simulate in our. So these are called slab calculation. Yeah, these are called slab calculation. It's a time consuming calculation, but we can do it. Yes.
Any further questions? Well, with that, let's thank VP again for that very, very interesting. Very nice.
Thank you very much. I appreciate. Thanks a lot.